Well, I think we should begin. So it gives me great pleasure to introduce Tim Jupp, who is going to talk to us about planetary climates and why atmospheric dynamics matter. Thank you.
Thank you. Thank you very much, Robert. Thank you very much, Philip, and the organisers of this meeting. It's an absolute pleasure to be here for my first visit to Canada. I very much hope not my last. It's been a terrific meeting. I've enjoyed it very much, so thank you very much indeed. Okay, so I'm going to talk about MaxEnt and planetary climates. Now, the groundwork for all this was prepared very nicely by Ralph in the first talk this morning, and in fact, you'll see some figures again that you saw in Ralph's talk, because they really are the classics in this field. And the overriding question is very simple to state. So Ralph had this business where he had two boxes representing the equatorial region of a planet and the polar region. And he was interested in the rate at which energy was transferred from the equatorial region to the polar region. And as if by magic, MaxEnt, or MEP, maximum entropy production, seemed to give him the observed answer. Now, if you're any kind of physicist, you find that fascinating. You also find it a little bit troubling, because you say to yourself, well, what's going on here? The atmosphere has all these complicated motions whose net effect is to transfer energy from the equator to the poles. And people who model this kind of thing for a living, including lots of people in Exeter, would say that the dynamics of what controls atmospheric motion must matter here. I mean, they say that because it's their life to care about atmospheric dynamics. But just intuitively, if you think about the different sorts of planets you might have, as Ralph mentioned already, some might spin faster than others. Some might be more massive and have greater gravity. They might have different solar constants. All these sort of things seem to matter even at the macroscopic scale. So what I want to do in this talk is ask the question why it is that we seem to get the right answer with such a ludicrously simple model. I mean, with no offence at all implied, it's almost a non-model, but it seems to give the right answer. So let's have a little think about that. Everything I'm going to say today, technically, is summarised in a paper that Peter Cox and I wrote last year, and please do go away and look up the gory details if you're interested. Now, we've already touched on this idea today that we need to be very, very careful what sort of entropy we're talking about. And we need to be very, very careful about minimization principles and maximization principles. So I'm going to take a little bit of a wander through the terminological minefield, and I'm going to define the terms that I'm going to use in this talk. I think the most important thing to focus on is the difference between information entropy, which I shall call S sub I, and thermodynamic entropy, which I shall call S. And of course, the big difference between those things is that information entropy is a dimensionless quantity to do with distributions, and thermodynamic entropy is a physical quantity with units. And I know we're going to have a talk tomorrow morning on the link between thermodynamic entropy and information entropy, and I'm very much looking forward to hearing that. So that's one thing. We've also got this business of what does entropy get used for, whether we're talking about the information entropy or the thermodynamic entropy. So Boltzmann and the second law would say that if you're moving from one equilibrium state to another equilibrium state, then the one you end up with as time moves forwards has greater thermodynamic entropy. That's fine. This whole meeting, of course, is based around Jaynes's MaxEnt sort of formalism, which is to do with assigning probabilities to microstates according to the information entropy. We've already heard about Roderick Dewer's work, which attempts, in the most successful way yet achieved, to link maximization of the rate of thermodynamic entropy production, which might be S dot, with the information entropy approach of Jaynes. This is what we've been talking about all day, MEP, maximum entropy production. And I'd just like to take this opportunity to request that any people in this room who think deeply about these sort of issues, who haven't looked at Roderick Dewar's work, please do so. I think it's fair to say that we all feel that it's very close to proving the link between these two formalisms. I think Roderick himself would say that it's not quite there, but we feel we're tantalizingly close, and we'd love it if some of the smart people in this room thought a bit more about that problem. And then just to throw in another one, Ilya Prigogine often talks about minimum entropy production, just to make life even more complicated. And I shall touch on that a little bit later in this talk. Okay, so we've got these two different types of entropy, and it's always useful to have a conceptual picture in your mind about what we're talking about. So, in the case of Boltzmann and the second law, the classic paradigm is to think about molecules of gas in a box. And they jiggle around, and there are all sorts of different microstates for the gas that look the same macroscopically. That's the important point. Now, so gas in a box is an equilibrium system thermodynamically, and it's closed because there is no flow of mass or energy across the boundaries. Let's contrast this with a non-equilibrium open system. Now, the picture I've got here is supposed to represent convection of a fluid or a gas inside a box. So it's not in thermodynamic equilibrium because there is a flow of energy from the bottom to the top. The bottom is hot, the top is blue, and it's open because there's a flow of energy. Now, these little arrows denote convection cells. We've already talked about self-organization into convection cells. And this profile here denotes the sort of temperature profile you get in a convecting fluid. So near the bottom of the pan, it's hot, and then there is a thin boundary layer in which there is a sharp gradient in temperature. You then get into the bulk of the fluid where all the convection is happening, and there isn't really much of a gradient in temperature. Then you get to the top, and there's a big temperature gradient again because you're at the boundary. So those are the two pictures to have in mind. So just to ram the point home, thermodynamic entropy, I call it S, has units of joules per Kelvin in SI, and the whole point, we all know this, but let's just do it one more time, is that all these hypothetically different boxes of gas look the same macroscopically, but there might be omega of them. So there are omega different microstates that all look the same on the big picture. So you define the entropy of the macrostate to be Boltzmann's constant times the log of the number of equivalent microstates. That's fine. There's also the more engineering way of looking at thermodynamic entropy, which just says if you have some body at absolute temperature T and you add a small amount of energy in a reversible fashion, then you increase the entropy inside this box by amount of energy added over absolute temperature. Fine. Now, entropy production. This is what MEP is all about, maximum entropy production. This looks rather like one of the schematics Ralph has already had. We obviously think the same way about these things. So you have a hot reservoir temperature T1, a cold reservoir at temperature T2, some sort of heat engine or system connecting the two. There is a rate at which energy flows in watts between the two. And the rate of entropy production is proportional to the rate at which energy flows from the hot bit to the cold bit times this little section here, which if you want to think in terms of integrals, is a volume integral of a flux. It's a flux of energy from left to right times the force that is driving that flux. And it turns out in thermodynamics that the relevant flux is the spatial gradient of reciprocal temperature. So the whole point about all this stuff is that if you were concerned about maximizing a rate of entropy production, then in very hand-wavy sort of terms, you're interested in how the flux, what's pushing energy through the system, the force, what pushes energy through the system, relates to the flux, how quickly energy does flow through the system. So there's a trade-off between these two things. If I have a very small flux, but a big force, I might get a small entropy production. If I have a very small force but a very big flux, I'd have a small entropy production. To get a big entropy production, I want both of these things to be relatively big. That's the trade-off that operates here. And finally, I just wanted to go back to the Shannon entropy. I often give this slide when I'm giving this talk to less well-informed audiences than you, but I didn't take it out because no one has mentioned this yet. In the Jaynes book, there is a section on what he calls the Wallace derivation, which I guess is familiar to a lot of you, which I find utterly intuitively convincing. But I'll just go through it quickly in case any of you don't know it. So the idea is that there are lots of different microstates the system might be in. We want to assign probabilities to these different microstates in such a way that we restrict ourselves to those microstates that are compatible with some macroscopically reproducible macrostate. And in the Wallace derivation in the Jaynes book, he says, well, you've got total probability 1 that you want to assign across microstates. So chop your unit mass of probability into a very many small quanta, and then scatter those quanta in some sort of random way across the microstates. That'll give you a distribution. And then what you care about with this distribution is whether or not it satisfies your macroscopic constraints. And in this example, I'll suppose that that means I want the distribution to have some specified mean and some specified standard deviation. So I do this random scattering. Sometimes I satisfy the constraint, sometimes I don't. I keep those distributions that do satisfy the macroscopic constraints. That's what this is supposed to show at the top. Some of these distributions do satisfy, that one doesn't. And it turns out in the limit, when you have many, many, many different quanta, you end up with distributions being arbitrarily close to the MaxEnt distribution, the one that maximizes the information entropy. There we go. So that one's no good, but all of these ones are tolerably close to the MaxEnt distribution. So a logical way to assign probabilities to a set of microstates. Okay, so the idea in closed equilibrium systems, if we had some blue gas and some white gas, is that if you remove the partition, there's a gradient in concentration which gets smoothed over time. There is production of entropy over this time interval, and we end up in a final equilibrium state which has maximum entropy. But the second law says nothing about how quickly this process takes place. We're interested in how quickly systems produce entropy. So we're going back to the example of convection in a box, which is often called Rayleigh-Bénard convection. I could say here that this was really where I first got interested in all of this maximum entropy stuff. For my PhD, I was looking at convection actually in porous media, but it doesn't matter. And I discovered that I could get the right answer for this convection on a macroscopic scale if I magically applied some principle of maximizing the total flux through the system. And this is something that fluid dynamicists have been thinking about for quite a long time. There are maximization principles that say if you have turbulent convection, then for reasons that nobody quite understands, the state of convection that you actually observe is the one in which the heat transfer from bottom to top is the greatest allowed by the physics. The physics don't, by themselves, tell you what state you'll see. But it is an observation that the state you do actually see is the one in which heat flux is maximized. Okay. Anyway, the point with these convection examples is that they are parameterized by a single dimensionless number called the Rayleigh number, which is proportional to the temperature difference between the bottom and the top. And what happens if the Rayleigh number is below a threshold is that you don't get convection in your box of fluid. So the temperature profile is just a straight line, and the only mechanism for heat transfer is standard conduction, as if this were a solid, not a fluid. However, when you exceed a critical value of the Rayleigh number, convection begins, there is structure formed, we get the temperature profile which I mentioned before, so sharp gradient, hardly any gradient, sharp gradient. And we might observe that the rate of thermodynamic entropy production is positive and quite big in the boundary layers, but essentially 0 in the bulk of the fluid. So, in our non-equilibrium example, as a function of Rayleigh number, we could say, what is the rate of entropy production? Well, if there were no convection at all, so if the fluid just stayed still, if we weren't in a gravitational field or something, this is what you'd get. This is the rate of entropy production as a function of Rayleigh number. Rayleigh number, remember, is turning up the gas on your cooker to make this thing operate more quickly. However, what you observe is not that, it's this. So you go beyond the critical Rayleigh number, and the rate of entropy production is much higher. And you might speculate that this is an example of maximum entropy production, MEP. Now, very quickly and very speculatively, I want to mention a semi-hypothesis I have about what on earth minimum and maximum entropy production mean. So I invite comments on this. So there are all sorts of states that a system might be in. And let's think about convection of fluid in a box. We might as well. And for each of those system states, there is an entropy production. Now, I've drawn this with lots of wiggles in. And if I understand it correctly, and I'm not entirely sure that I do, Prigoghine's minimum entropy production says that local minima are steady states. So these green points are steady states of the system, and the bits that aren't local minima would be unsteady states of the system. Now I wonder if maximum entropy production is a selection procedure amongst steady states. So what Roderick Dewar might be leading us towards is this idea that the MEP state, which is the one you actually observe, when you repeat the experiment, you make it macroscopically reproducible. All right, these things are steady states, but the one you actually see is that one. So I have this, my half idea is that the MEP state is the biggest of the minima. But that could be complete rubbish. I have no idea. Okay, so the challenge, and the challenge I would love it if people in this room took up, is to link information entropy, distribution of microstates, with the rate of entropy production, thermodynamic entropy production. Okay, so let's get on to the specific example of climate. Now, we've already talked about Ralph's paper in Science, which I recommend. There was another one in Nature called Order Out of Chaos, 2005. Well worth looking at. I hardly need to say it to this audience, but the Jane's book is very much recommended bedtime reading. We've also seen this already. Axel Kleiden and Ralph Lorenz's book, which as an overview takes a very big picture thermodynamic view of what happens on planets. I think my next slide might even say this. Yeah, so this is from that book. The whole philosophy we're going to adopt here is stepping right back from a planet and looking at it in the simplest way we can, consistent with the question we want to answer. And the thing to bear in mind is that at this level of complexity, what does the planetary atmosphere do? Well, it takes in radiation from the sun, which comes in at about comes from a body at 6,000 Kelvin. And then there are various processes. Radiation is absorbed at the Earth's surface. That radiation absorbed by the Earth's surface goes into heating the atmosphere, which drives convection currents, is then re-radiated back into space at the top of the atmosphere at about 250 Kelvin. And if you sort of track this energy all the way through, it ends up in space at 3 Kelvin. That's the kind of attitude we want to be taking. So why might MEP be useful? Well, I'm going to show you in a minute a couple of examples where people have had apparently free parameters in their models. They cook up models for the atmosphere, and then there are always little parameters in your model that you can tweak. And that's half the fun, really, of running numerical models. You can just double some parameter and see what happens. But there's the observed value. When I say best value, I really mean the value observed in nature. And we have this sneaking suspicion that if you try tweaking these parameters away from their observed values, you'll move away from a maximum in entropy production. Now, why is that useful? I think it's useful because it might tell us when our model is sufficient, when our model contains enough physics to encapsulate all that we are trying to model. You might speculate that if we can't go through this procedure, if we find that the parameter value observed in nature does not maximize entropy production compared with all other possible values, then our model doesn't have enough physics. We forgot to put a constraint in. We forgot to conserve momentum. So I think this is a very important point about modeling. You're constructing a vision of reality. Well, what's instructive is to think about exactly what you have to put into your model to get the right answer. So when we model the atmosphere, we don't worry about the gravitational attraction of the cup of tea on my desk, clearly. But a good question to ask is, how much do I have to put into my model to get the right macroscopic answer? So we're going to think about models of the atmosphere because we want to take Ralph's box model and put some plausible physics into it. So this is a Mark I atmospheric heat engine, just about the simplest thing you could think of beyond solely conserving energy. And this just contains the physics, the physical balance, that there is a force because hot air rises, and that is balanced by surface friction. So this Mark I heat engine would give you Hadley cells, as they're called, which are convection cells in the atmosphere that go like that and transfer heat from the equator to the poles. Now, you'll notice that there's no mention here of the planet rotating, and everybody has this hunch that rotation of the planet matters. So let's allow that. The Mark II atmospheric heat engine simply adds in a Coriolis force. That's a force that arises because planets rotate, and it means that things turn to the right in the northern hemisphere and to the left in the southern hemisphere. So this is a minimal model that seems sort of plausible. And there are only three things in it, really. Hot air rises, there is a Coriolis force that deflects things, and the frictional force comes from the friction between winds and the surface of the planet. So I just want to emphasize that what I'm going to talk about, this model here, lies on a spectrum, and it lies in the middle of a spectrum. So Ralph's model that we've heard about already contains no dynamics whatsoever. Just has boxes for the equator and the poles. Axel Kleiden ran a model that I'll tell you about in a minute, which was a full numerical model of the atmosphere. And he had a parameter in it which he tweaked, and he found that the observed value maximized entropy production. What a surprise. And I wanted to be somewhere in the middle. I wanted to have a model that I could write down and solve almost analytically, but I wanted to make sure it had some dynamics in it, just to see what would happen. So you've seen this before. This is Ralph's model, which just says there's a tropical region, a polar region, incoming solar flux, outgoing radiation, and some unknown flux between the equator and the poles. It has no dynamics. But the equator to pole flux is a free parameter in this model. It's something we can tweak. And we found rather convincingly that if you tweak it to maximize entropy production, you seem to get the right answer. I don't think I want to go through this in any great detail, but the point I want to make is that I shall talk about LEB solutions. They're Lorenz energy balance solutions. These are the solutions you would get with this model here. Okay, if this was your model of a planet and you tweaked F to maximize entropy production, you'd get a solution which I will call the Lorenz energy balance solution. There are some technical details here that I don't want you to worry about too much. To make my life easier, I've linearized the Stefan Boltzmann law for how outgoing radiation depends on temperature. It turns out there are some natural scalings here. Something I was very keen to do in constructing this model was to non-dimensionalize it. That's just a product of the way I was brought up academically. I had it beaten into me as an undergraduate that the path to enlightenment was paved with dimensionless numbers. And it's very hard to step away from that kind of thing. So the only important thing you need to know is that this is my dimensionless entropy production, and I've scaled it all so it can be between 0 and 1. And these F is a dimensionless flux from equator to pole. Sub A means atmospheric. T is a dimensionless temperature, and the subscript EP means a difference between the equator and the pole. And it so turns out that the rate of entropy production, when suitably non-dimensionalized, is the product of the flux and the equator to pole temperature difference, which is the driving force for that flux. That's what we saw before. In the Lorenz model, when we non-dimensionalize it, the idea is to maximize this entropy production subject to a sole constraint of energy conservation. And it turns out to be that the constraint becomes that the sum of the flux and the force, the equator to pole temperature difference, must be 1. And it's very easy to write down that the Lorenz energy balance solution is then a entropy production of 1 when both the flux and the force are a half. Okay, you've seen this before. This is what happens. There's the equatorial temperature as a function of our free parameter. There's the polar temperature. This is the entropy production, and if we maximize it, we get that. So that's out of all our candidate steady states, that's the favorite one. We saw it for Titan, we saw it for Mars. Okay, so that's great. So MEP, maximum entropy production, seems to give us the magnitude of the flux that we observe in real life from a model containing no dynamics. Well, that's terrific, but why? This can keep you awake at night, this stuff. Surely the atmospheric dynamics matter. Surely planetary rotation matters. Okay, I'm now going to go to the other end of the spectrum, a complicated numerical model. This is Axel Kleiden published this. I mean, all numerical models show you much the same thing. This is just a gratuitously pretty animation. But what Axel did, and it takes courage to do this, I've written von Karman parameter. It's actually the von Karman constant. It's a number that parameterizes the amount of friction between the atmosphere and the surface. Now, you might feel a bit giddy taking a constant and varying it, but Axel didn't care. He just did it anyway. So he ran this model for different values of the von Karman constant, and he just looked at the entropy production that he could diagnose from the output of this numerical model. Now, ignore the dotted line, that's not relevant. This solid line is the entropy production in his great big numerical model as a function of this von Karman constant, whose true value is 0.4, somewhere there. So out of all these candidate steady states for different von Karman constants, it turns out that the true von Karman constant maximizes entropy production, which may mean nothing at all, but it's certainly intriguing. MEP seems to give the right answer yet again. So, in a model containing a lot of dynamics, MEP seems to work. That's terrific. But why? Goodness me, why? Which model parameters are important? How does the surface friction predicted by MEP change between planets? So let's get on to our model now. So what we did was we took the equatorial region and the polar region that Ralph thought about, but we sort of rarefied them a bit more into regions of a spherical planet whose sun lies on the equator, just to make life really easy. We've deliberately put the boundary between these two things at 30 degrees latitude. That just means that The surface area of these two regions is the same, which makes life a lot easier. Our planet will have a radius big R. It will have an atmosphere of thickness big H. It will rotate at speed capital omega. And we'll assume that a wind is set up that blows, at least on the surface, from the polar region to the equatorial region at speed u and at an angle theta to the straight north-south direction. So you can imagine that as you crank up the rotation rate, this wind would get deflected more and more away from running straight north-south. We'll cook up some equations, we'll solve them, and we'll treat something called the surface drag coefficient as the free parameter, as the thing we're going to tweak. This is essentially the same as tweaking the von Karman constant, but it means we don't have to vary a constant, which makes me feel better. So here's a schematic for what we're doing. There's the surface in the equatorial region, the surface in the polar region. The dashed lines are radiative fluxes. So a radiative flux comes into the equatorial region, and it's bigger because of geometry than the flux that comes in from the sun to the polar region. There are outgoing fluxes, which I have linearized to be linear functions of the surface temperatures. Then we have this magic equator to pole flux, FA, and by energy conservation it's the same there as it is there as it is there. We have this surface wind, whose north-south component is u cos theta, because it blows at an angle theta to the due south direction. And of course, a surface wind has to be balanced by a corresponding wind high in the atmosphere. That's what this is supposed to mean. I've got my surface temperatures, and up here, I've got temperatures for the atmosphere. It turns out there's enough symmetry in this problem. T sub SA means a surface to atmosphere temperature difference. That's all it is. So there's a difference in temperature between the surface and the bit of atmosphere immediately above the surface. And of course, in the equatorial region, the atmosphere is colder than the surface. In the polar region, the atmosphere is hotter than the surface. And all we've got to do now is work out some plausible, simple equations for how all these things relate to each other. Okay, don't worry about the details. The details are all in the paper if you want them. But we're going to have conservation of energy, just as Ralph does. We then want to have an equation for the surface to atmosphere flux. So in either the equatorial or the polar region, there's a drag coefficient, and we've got an atmosphere with a particular heat capacity and density. The wind blows on the surface at speed u, and there is a surface to atmosphere temperature difference T sub SA. So the simplest thing you could write down is that the flux of energy from the planetary surface to the atmosphere above it should look a bit like this. Then we've got the equator to pole flux. So this is the flux that operates in the atmosphere between the equatorial atmospheric region and the polar atmospheric region. We've got some pi r squareds in here just because of geometry and because we want to normalize by surface area. But this flux is proportional to the radius of the planet, the thickness of the atmosphere, because this wind blows through a particular thickness of atmosphere, the heat capacity, u cos theta this time, because in transferring energy by advection from the equatorial to the polar region, we only care about the north-south components of wind. Any east-west components of wind doesn't transfer energy across the boundary. And again, we have to multiply by the appropriate temperature difference between equatorial atmosphere and polar atmosphere, and that turns out to be that. Finally, we've got our dynamics terms. So for those who are into this kind of thing, we've got quadratic drag. So there are two equations here because one operates in the north-south direction, one operates in the east-west direction. And this drag in both cases is sorry, just have a little pause while I think about this. The important point is that this is what drives the motion. There's a g here, a gravity. So Convection only takes place in a gravitational field, and that is why we have a G here. I'm hesitating because I've suddenly realized I can't quite remember what all this means. It's in my paper. I went through it 100 times. I'm pretty confident about it. But we'll come back to it later. Okay, the point is this system is just simple enough that we can pretty much obtain analytical solutions, with a numerical solver occasionally, with the surface drag as the free parameter. Right, so for any particular planet, you've got all these things that specify what the planet is. Here's a little dial that we can tweak to vary the surface friction. When we solve those equations, we will get out things like the surface temperature, the wind speed, the direction in which the wind blows, and the magnitude of the flux. And we might ask ourselves, out of all these solutions that we get for different drag coefficients, which one maximizes the entropy production? That would be the entropy solution. But also a separate question, which solution would maximize the atmospheric flux? I put that one in because all the sort of fluid dynamics literature about convecting fluids doesn't talk about entropy production. It talks about fluxes. And these two things are similar but different. And we could ask the question, what's the difference between a maximum atmospheric flux solution, a maximum entropy production solution, and remember there was the LEB solution, the Lorenz energy balance solution that you get by ignoring all of these equations except the top one. So the three types of maximization principle I might apply. I said I was into non-dimensionalization. It turns out when you do all the work that there are really three dimensionless parameters that describe each planet in this system. This thing at the bottom, gamma, is just a geometric constant that comes out of the way it all works. The stuff in the square brackets is what matters. The stuff in front of it is just pre-multipliers. I had a long think about what these dimensionless parameters mean. I think of this psi thing as being the advective capacity of the atmosphere, because it has in it the heat capacity of the atmosphere. It has the thickness of the atmosphere, and you can imagine that a thicker atmosphere with a bigger heat capacity would be more able to transfer energy by advection. And of course what drives advection is gravity. That's why gravity's in there. Eta, which turns out not to matter that much, is simply the ratio of the atmospheric thickness to the radius of the planet. And then down here, omega is a dimensionless version of the rotation rate of the planet. Remember, r was the radius of the planet. Root gh is a sort of fluid dynamic wave speed. Okay, so what happens as a function of these dimensionless parameters for an arbitrary planet? Don't worry about the numbers. Just accept that for Earth, Titan, Mars, and Venus, you can look up on the web somewhere values for all the dimensional parameters and then turn them into values of all the dimensionless parameters. So here's an example. What happens for Earth? So we're going to vary the drag coefficient, and the true value of the drag coefficient is of order 1, so it's about there. When we solve this system, this is what we get. So the dashed line is the angle at which the wind blows. So that's the right-hand scale. So when the angle is 0, the wind is blowing north-south. So that's out here. High drag, wind blows north-south. As I reduce the drag, there's a point at which the wind blows at 45 degrees to meridians, and then I reduce the drag right down, and I end up with an east-west wind. We can see that here. This thing I've called speed is u, the total wind speed, whose components are the east-west component and the north-south component. So you can see that the north-south component of the wind is maximized about here. That's the kind of thing we can get out of this. Now, sorry, this is a bit of a busy slide, but I'll try and go through it. These are the sort of thermodynamic bits of the solution that you get out. Which one should we go for first? Let's go for the dashed line. So this is the flux. Okay? the flux from equator to pole, and as I increase the drag coefficient, there is a maximum in flux. That's the maximum atmospheric flux state. And then, of course, it goes down. Now, remember, there was this energy balance constraint, which said that the equator to pole temperature gradient plus the atmospheric flux is always 1. That's what energy balance says. So complementary to this atmospheric flux is this one here, which is just 1 minus the atmospheric flux, which is the equator to pole temperature difference. And we said that the entropy production was essentially the product of these two things. And we said that the greatest possible entropy production is 1, and that occurs when both the atmospheric flux, that's this one, and the equator to pole temperature difference are a half. Now, there we go. So the Lorenz energy balance state, which is a scaled entropy production of 1, is also the state which maximizes entropy production. Here's entropy production as a function of surface drag. So some interesting remarks here. Firstly, the true value of the drag coefficient in this case seems to give me a state of maximum atmospheric flux. Remark number 1. Remark number 2, I seem to maximize entropy production in 2 places. And there's no obvious reason to choose between them in this model. But let's observe that in this case, adding in the dynamics did not prevent the system from achieving the entropy production that Ralph Lorenz would have predicted, the LEB state. It is possible for this planet, in my model, to get to an entropy production of 1. All right, for 2 implausible values of the drag coefficient, but that's what we observe. I'm going to show you the results for the other planets. I mean, essentially, they're much the same. The numbers are a bit different, but the principle is the same. So for Venus, same thing. There are 2 points at which I can achieve what Ralph would have predicted. And there is 1 point in the middle at which I would maximize the atmospheric flux. Same thing for Titan. Almost the same thing for Mars. Mars is sort of on the boundary of what's going on. Oops. These 2 MEP states have almost coalesced. The reason they've done that is because the maximum atmospheric flux that I can get in this model is nearly 1/2. And a flux of 1/2 gives me an entropy production of 1, which is the biggest possible. So we wanted to understand this a bit, so we thought, well, let's have a little think about what would happen for arbitrary planets that might have essentially any rotation rate when non-dimensionalized, and essentially any advection parameter when non-dimensionalized. And because we can solve this system, in this we can draw contours of what the entropy production is at MEP. What is the greatest entropy production that these planets could get to when dynamically constrained? Okay? Now, it turns out when you do this that above this dashed line, which I've called the critical line, planets who live in here are able to achieve an entropy production of 1, even when dynamically constrained. So the dynamic constraints don't prevent them from getting to this Lorenz value of entropy production. However, if I had a planet that lived down here somewhere, for example, if it lived here, then the dynamic constraints just mean in this model that the largest entropy production you can get is 0.1. So where do Earth, Mars, Venus, and Titan live on this diagram? Well, they live here. They live pretty much above, well, they do. They live above the critical line. Okay, so these 4 were the 4 we thought about before. This is the line above which our model does not prevent entropy productions of 1. Below the line, you cannot get an entropy production of 1, and so we invented a fictitious planet P1 just to make the point. But one might imagine that out of all those thousands of exoplanets that people have discovered, one might have planets that live all over this state space. So yes, below this critical line, the inclusion of dynamics affects what the entropy production is at MEP. And we've drawn in this other line, which is a dimensionless rotation rate of 1. And the interpretation of being left of this line or being right of that line is that for dimensionless rotation rates greater than 1, rotation matters to the MEP state. Okay, so I wanted to sum up these different maximization principles that you might have. So a maximum atmospheric flux approach, you just say, let's maximize that. In my language, that means you maximize FA, and you would apply constraints of energy conservation and plausible dynamics. In Ralph's example, you're maximizing entropy production subject only to energy conservation, in which case you can write down an explicit solution, which is this, and MEP, you maximize entropy production subject to both energy conservation and dynamical constraints. So this is just a restatement of what I've already said. I've gone back to the sort of language that Ralph used in his talk, where the thing that you're tweaking is this sort of diffusion coefficient that says how easy it is for energy to go from the equator to the pole. It's the thing we might tweak. For some planet, you can work out the entropy production, the flux, the driving force as a function of this tweakable parameter. And all we're saying is that depending on the planet, there is a line here above which high diffusion constants are deemed dynamically impossible. Now, getting an entropy production of 1 corresponds to being here. So what matters here is whether or not this constraint line, dividing dynamically impossible from dynamically allowed, allows this peak or not. That's the argument. If the dynamical constraints allow the peak and allow you to get to an entropy production of 1, then we would assume it would happen, but they might not. Okay, so let me summarize. I hope that we've given some insight into Axel Clyden's numerical result with the big climate model. We took Ralph's no dynamics model and we've sort of reinterpreted it as the limit of a dynamical model. And we hope that we've given some insight of why rotation and atmospheric dynamics do matter. It just so happens that they don't particularly constrain things for planets in the solar system. I will finish. We good for time? Yep. With a remark that I mentioned at the beginning, that MaxEnt, or maximum entropy production, if you want to call it that, is useful for people like me because it can tell you when your model contains just enough physics. It's a sort of diagnostic tool for whether your model is capturing what you want it to capture. A secondary point I want to make is that I always think about this when I try and think about linking information theory to fluid dynamics or this kind of applied physics stuff. I always think of people like Shannon working for telephone companies. And so the picture I have is of someone picking up a telephone and phoning up somebody else and conveying information to them. And I think the key point about all this stuff is how much do I have to tell you over the telephone for you to be able to reproduce the planet I'm thinking about? You could draw an analogy with file compression, optimally zipping your files. It seems to be that if I want to tell you about equator to pole energy transport on Earth, I don't really need to tell you very much. I just need to tell you the stuff that's in Ralph's model. But for some other planet, some as yet undiscovered planet, it may be that in order for you to reproduce the macroscopic view of the planet that I'm thinking about, that I have to tell you more over the telephone. And I'll stop there.
Thank you, Tim. Questions?
Thank you very much for a stimulating presentation. I just wonder, one of the features that's so prominent around the Earth are the winds that run from east-west and west-east. That is, you know, the trade winds running around the equator, and then the jet stream that runs so high, so it takes much longer to get from Toronto to Vancouver than vice versa. And I'm just wondering whether, it wasn't clear to me, but maybe it was, whether these winds, these steady winds of pretty high velocity, especially the jet stream, come out of your analysis or not.
They don't. So the model I formulated has no concept of jet streams. And I defend that simply by saying that I get the answer I wanted without having to bother about jet streams. And maybe if you wanted to describe some other aspect of the Earth's atmosphere, well, obviously you do need jet streams. So I think that's an example of how much do I need to put into my model to get the answer I want.
Do you have any clue as to what you might have to put in order to explain the jet stream?
To explain the jet stream? I'd like to think about that.
Okay.
Any more questions?
Yeah, I would turn this question around. Instead of saying how much, I would turn the question around. Instead of asking how much physics do I need to input the model to get the correct answer, I would ask, just given certain physics, what's the best can we do? I think that's, as I understand, that's the Bayesian inference idea. So you may not get, I feel you may not get definite answer, but if you turn around, you can get definite answer. I don't mean you get certainty, but you know what the best you can do from using the Bayesian formulas and framework, the idea, analysis. Because we may not know what's the enough, how much is enough.
It all depends what question you're trying to answer. Right?
Yeah, but it's well-defined the problem, saying, given this, what's the best we can do?
That's true, that's one question, but maybe I should have been more explicit. So the question I wanted to answer was, why on earth does Ralph get the right answer from his model? That was the question I was interested in.
And why on Titan as well?
Yeah, yeah.
John?
No, give it to Ariel first.
All right. Ariel.
Yes, this is a comment on the last question. It was a very good point, but I would like to point out that there are two problems involved. One is, on the basis of the available information, what is the best prediction we can make, which may not be any good at all. It's going to be the best, but it may not be any good at all. And there is the question that you are trying to answer, which is a very legitimate question, and for the purposes of doing physics, it is the right question to ask, because we would like to know that our answers have a chance of being correct. So identifying the relevant information for a particular problem is one of the goals of the whole enterprise. So I very much identify with the approach that you have taken. I like that.
Okay.
Thank you.
I was wondering if you had thought about considering, instead of a marginal description of your phenomenon, a time exploded a description of your phenomenon as a sequence, because if you look at a sequence, you can define what's called the entropy rate, and basically the law of large numbers tells you that if you just look at the marginal density, you will only see typical sequences, but they have no time structure. Now, if you have a constraint on your time structure, such as, for example, causality, you may get something very interesting, something that really fits your model. For example, I was telling, I think Ralph was telling about this, and there's some literature in, I think from the 70s, or if I'm not mistaken, looking at spectral estimation. So people use AR models, autoregressive models, and it's been proven that the autoregressive model satisfies the maximum entropy principle. And so people have been looking at time-constrained maximization of entropies. So I was wondering whether you had any.
I'm afraid I don't have much to add on that. I'd be very interested to hear more detail about that. I mean, something I
no expert, but yeah, I heard.
So something I forgot to say there's the particles of gas in a box paradigm, and the point is that you can do statistical mechanics on that and derive the gas law. So you don't have to model each little billiard ball to get the gas law, you just use the gas law. And we would love to do something similar for systems through which energy is flowing. And I wonder what the simplest example is. Perhaps it's particles of gas in a box in a gravitational field with a temperature difference applied.
I agree with you totally on the meaning of entropy as Wallace's.
Yeah.
I agree with that totally.
Just briefly following up on something that Francesca just said then about autoregressive models in the 70s, just reminds me that the whole area of Box-Cox time series modelling, autoregressive moving average and ARIMA models was co-invented by George Box and George Chow, and George Box, G.E.P. Box, is famous for several things. He's one of the most famous American industrial statisticians. He married Ronald Aylmer Fisher's daughter, who wrote a book about Fisher. And George Box said something I think just should be mentioned once in this room this week, which was that all models are wrong, some models are useful.
Indeed.
More questions?
Yours is useful.
Thank you.
That always helps when it's useful. I just wanted to point out something to make a comment on when you brought up the idea of the flux, and you were saying if they compared or whatever. So Dewar gets some of his stuff from Jaynes, obviously from Jaynes's what he calls the caliber.
Yep.
And so in Jaynes's ironically titled paper, Minimum Entropy Production, he mentions that these microstates now are moving in time, so you have world lines, and that the entropy he considers as a cross-section of this tube of world lines, which would then be a flux. Right? So perhaps that's coincidental, or perhaps that may be some interest to it.
That's sort of what Roderick Dewar is working on at the moment.
Sort of, yeah.
Yeah.
When you maximize the Shannon information entropy, you maximize the missing information in your model. Therefore, your model, all of the physics in your model, you were sure that you had no hidden lurking information that you didn't want in your model. So, in a sense, maximum entropy is sort of a negative principle, in that it's an insurance policy that excluded anything that you didn't want in that full physical model that you presented.
Yes, I agree with that.
Okay. So there's no reason to expect that there was anything else other than what you put in.
Well,
I'm sorry?
I suppose what people in our community have done is that we've taken this idea of maximum entropy production, which is sort of almost proved to be equivalent to MaxEnt, and we all believe it, we think it's great, and we apply it. So we build models that we think are physically reasonable. So that's our assumption, that we've put in sensible physics, and we see if they work. If they don't work, we try again. But I don't claim any more than that for what we're doing.
Any more questions?
So
John Skilling. Sorry?
We'll just ask a question. Just to understand it, what you're seeing in the experimentation is that you always have point-wise maximization of the
derivative of the entropy.
Could you say that again? Sorry.
So point-wise, if you take a picture in time, you see maximization of the derivative of the entropy.
That's what we think. Yeah.
At least that's what you at least see in the experiments.
That's right. So in a numerical experiment with a climate model, you can tweak a couple of lines of code and get it to spit out the instantaneous rate of increase of thermodynamic entropy. And you can see what that is as you tweak the dials.
Okay.
Sorry, it's a steady state rate though, isn't it? It's only a steady state model.
Well, it depends which model you're talking about.
Okay. Yeah. Your model that you put.
Oh, my model, yes, it's steady state. Absolutely. Completely steady state.
Yeah. So I don't think anybody has gone beyond steady state.
Yeah.
So Roderick Dewar is trying to do so, but yeah. So John Skilling wants to have the last word. I just wanted to make a couple of comments. I just wanted to thank you, Tim, for your presentation and clarification of many of these things that people have been talking about in this EP field. So thank you for that.
Thank you.
And you saved me a lot of trouble for my presentation. So I can take out significant chunks, which is good. I have a homework problem for you.
Oh no.
This is something that we need to talk about. You presented essentially a 2-box model. We need an n-box model, and which incorporates planetary rotation, and can we do that? So that's
okay. We'll work.
That's your assignment for tomorrow.
Thank you. I sat here this morning and I've been afflicted by an increasingly intense image of Edwin James, who would have been sitting there.
I'm so nervous about what you're going to say now.
Almost completely silent, because he would have been absorbing this, and I'm sure he would have been wishing that he had thought of thinking of it this way. He was extraordinarily successful, inspiring, in sorting out equilibrium statistical mechanics. He spent decades, and his colleagues spent decades, trying to sort out non-equilibrium statistical mechanics from the same sort of bottom-up microscopic states, and evolution and world lines, as you were saying. And really, basically, it never quite worked out properly. And you're taking the physics in exactly the sort of rough and ready way that he used for Wolf's Die and all these examples, and coming in and making it work. Ed James would have loved this. Thank you.
Thank you. Gosh.